So before I jump into slides, I want to let you know where you can get the slides and where you can get the source code. So it's the github.com/Kokkos. And we've got several repositories sitting in there. The main repository for the source code, to be able to clone that, and if you'll be doing the exercises tonight, you'll be needing to get there and clone it and bring it down. And then there is the Kokkos tutorials, which is where this tutorial and several other tutorials reside. So we've presented this at the GPU Technology Conference and Supercomputing for a couple of years now. So this is an encore performance of the last GPU Technology Conference tutorial that we gave. So if you go to that, and then there's the PDF right there for the slides, so you can get it yourself and follow along. This was including exercise time, a 2.5-hour tutorial. Minus all the exercises will be fine in the 90 minutes, and then tonight you can do the exercises. You'll be pulling them out from the Kokkos tutorials exercises. Okay, so as we go through this, there's going to be several stopping points where it says, okay, do this exercise. Well, since we're not doing the exercises during the lecture, we will just slide on through that time and describe what you would have gotten, and it will kind of spoil the surprise for tonight, but that's the format. Okay, let's jump in. Okay, NV, and there we go. NVIDIA sponsored that tonight. Okay, I hope everyone has got access for the exercises tonight, access to some machine they can log into that's got at least a Kepler GPU attached to it. And so if you have that, and CUDA, at least CUDA 7.5 or better, we're going to be in great shape for the exercises tonight. Okay, prerequisites. If you are not familiar with C++ already, the exercises are going to be extremely challenging because you'll be having to learn C++ and learn Kokkos at the same time. So you might want to take that into account when you come back here. So hopefully everyone in the room is familiar with C++. Once we do that, then you can go to GitHub, as we were showing you, and pick up the Kokkos source code, clone it down, and then pick up the Kokkos tutorials and clone that down as well. So what we want to do with this tutorial is make sure you have a good understanding of the basics. We're just going to go through, there's a kind of a basics and an advanced, and the half day or the 90 minutes, we'll just get to the basics. And I'll just mention the advanced when we get to the end, but we won't have any time to get into that, about how to get performance portability, the what, the how, the why of performance portability, and hopefully that you'll be convinced that the constructs we've provided in Kokkos give you future proofing, as in performance portability to architectures that are still not on the floor and are still evolving. And so far we've got some good proof points that we have been able to do that. The basic capabilities we're going to cover today: simple data parallel patterns, deciding where a code is run, how data is placed, how data is managed, so you can get correct data access patterns, and how important correct access data patterns are for the architecture you're dealing with. So some of the advanced stuff that is in the full day tutorial, if you go to the supercomputing tutorials, you can grab one. Talk about thread safety, thread scalability issues, because when you get on these GPUs, you're looking at tens of thousands of threads, genuinely concurrent ways of parallelism inside shared memory with a limited amount of memory. And atomic operations, which are very crucial for doing lock-free data structures and lock-free parallelism. Hierarchical parallel patterns, which is critical for getting a lot of getting performance on non-trivial kernels. DAG of acyclic graphs that you can run on a GPU. I won't get into that today either. And various plug-in points to be able to do extensibility. So you can talk to me about that during the exercises tonight. They can also be a consulting time as well as an exercise time. Okay, so for portability, we've got some programming models that claim to be portable. Well, you get OpenMP, and if OpenMP 4.5 kind of evolves and matures, and you get to OpenMP 5, you can get to the GPU and be able to use it and get things to actually run. OpenACC has done a better job with the GPUs, or there's also Kokkos if you're in the C++ realm to get it. One of the things that is special about Kokkos compared to these others, at least for the C++, and I'm going to quit harping on that now, is that it manages memory access patterns. And that is incredibly important to getting performance, not just can I run the code awfully on different architectures, but can I run the code well on the different architectures. So one of the objectives we've had from the very beginning, and this is for adoption and for people as they get into the system, is that things which should be simple should stay simple, should look simple, feel simple, and be simple to do. But once you start getting to very complex things, that the complexity is incrementally introduced as opposed to having to do some massively complex thing from the very beginning. Okay. This is from the GPU Tech Conference. We assume everybody who's at the GPU Tech Conference wants to use GPUs. Okay. So assumption for the on-node parallelism and the on-node target machine. It's kind of an abstract notion, and there's different pieces that come into play with different architectures, and this is kind of a trivialized cartoon of it, that we have different kinds of cores. We've got heavyweight, latency optimized, your conventional CPU cores. So we've got attached accelerators. They've got memory attached to those that these cores can't touch. And then you've got memory sitting there on package, or maybe some non-volatile RAM sitting out there, your DRAM sitting out there. You've got this whole network on a chip. You've got external interfaces. So you've just got all sorts of different kinds of compute potential, heterogeneous, and lots of different kinds of memory. And you've got to worry about, if you really want to get performance, you've got to worry about what data lives where and when, and who's going to touch it, and how they're going to touch it. So as I mentioned before, there's a strong difference between getting things to run everywhere, be truly portable. Can I just throw a OpenMP Pragma target and it'll run on a GPU? But how well? So we want implementations to be able to run and have good performance. We want one implementation. You can write one implementation and then compile it and run it on multiple architectures and get performance which is comparable within a few percentage, which is comparable to as if you had become an expert in that architecture and hand wrote it for that architecture. That's a tall challenge. Okay, let me get into concepts. This is a tutorial teaching very foundational concepts before we get into the actual exercises this evening on how to actually do that. So terminology, getting in here, and then the data layout problem. Okay, first concept is computations are composed of patterns, policies, and bodies. So I'm going to patterns, policies, and bodies. Okay, the pattern, in this case, in a simple illustration of a for loop over some elements doing some computation, the pattern is a for. We're going to apply some body number of element times. So the pattern is we're going to apply that number of element times. The policy is we're going to go from the number of element times is actually going to be from 0 to number of elements minus 1, and then we're going to call that body. So the pattern is the structure of the computation of for, parallel reduce, parallel scan, task graph. That is the pattern of a computation. Then you can plug in an execution policy. How are you going to do that? The simplest thing is static scheduling. I'm going to do this. I'm going to split it up among threads that are available and run it. Dynamic scheduling. You start doing work stealing between them. Or thread teams. How are you going to do this hierarchically somehow? And the computational body, the code which is going to be applied according to that pattern and according to that policy. So pattern, policy drive the computational body on the underlying hardware. So threading a parallel for, if you want to do this, if you're doing OpenMP, in theory, you can start off just by saying, hey, OpenMP, make it parallel. So now we've changed the policy from being a serial for to a parallel for. So OpenMP, you can do this. It's simple. Things stay simple. But what if we want to do this on some other architecture? So if you want to do a parallel for using OpenMP4 standard, and you want to take that loop that simple loop, and you want to do the policy pattern, the policy to be able to offload it to a GPU and run it. Now we start stacking up all of these pragmas. How do we map it onto the target? How do we do the thread teams underlying it? How do we get the number of threads? What variables are going to have to be private? What variables are going to have to be public? So it turns out for simple loops, so a color-coded, so we still have the notion that, oh, yeah, here's our pattern here, and then here's our body, and we've done some private stuff, and then here's our policies that are kind of spread out over. So it's still there. It's just fragmented everywhere. OpenACC, about the same kind of thing. You've got these policy stuff that was then spread around a bit. You've got some body things. You have to worry about data motion, so there's your body, and you still got your pattern. Okay, well that gives you some portability. That allows you to be able to take that loop and run it on a bunch of different architectures. But what happens with performance? Well, that depends on the memory access pattern that's going on inside that loop body according to policy and according to pattern. So memory access pattern. So, okay, for the moment we'll say that we can, summarize all this and stick the pragmas up there properly. And we have some non-trivial loop here. This is going to be a loop over elements, quadrature points, and then a vectorization here. So we have in a conventional C program where you have some arrays and you have some indexing computation to be able to access your arrays of data and then compute. Well, problem is that if you do this if you have this all nice and set up and tuned for a CPU, and you take it over the GPU, and you believe that, hey, the GPU's got all these cores and all this capability, and find out that it's actually running slower than it did on the CPU. And the problem is that the memory access pattern you baked in here was designed for a CPU cached architecture with vector units. But the GPU doesn't do that, and so it has a completely different memory access pattern. This is when you've probably seen or heard about this array of structure to structure array transformations, and when people have to go back and rewrite their codes. It's a royal pain. Okay, so Kokkos is going to be addressing all of these different issues in terms of usability, the pattern, policy, and body, be able to adjust memory access patterns so you don't have these slowdowns when you move from one architecture to another. It's also a library. When you download it, you're just using your conventional C++ or the CUDA, CUDA 8.0 compiler. By the time I get done, I hope that'll convince you it's very clear and concise about what's going on. Lets you write them algorithms once, minimizes the amount of architecture-specific code you have to do, and then it solves a data layout problem. And we'll be getting to that. So data parallel patterns, the details now. So pattern, policy, body. Details of that. Okay. So how does Kokkos look for this, or how does Kokkos going to do this when you have these patterns? So we consider the computational body to be the work. I mean, that's the actual work that's going to happen. Everything else is just driving the work, but the actual computations, the mathematics go inside the loop body. So each iteration is a unit of work. Iteration index, as in this index, that is a identifier for how many units of work in which particular unit of work, and then you have a total amount of work that goes in. So this work mapping is an important thing. So we have a body here, and we're going to map it onto the underlying hardware. But how do we do that? Well, Kokkos does that. So that way we have the freedom to map one way for CPU architectures, one way for Knight's Landing, one way for the Volta GPUs, et cetera. So that's why we separate it. You give an iteration range in the computational body and tell us what pattern you want, and we apply it. Okay, so if you're familiar with C++, the term functor, it's actually something simple. It's you make a struct or a class, you provide a void operator, and then some argument that says what unit of work, and put your computational body inside there. That is a functor. So then how do we assign work to functors? We have a Kokkos, parallel for, parallel reduce, parallel scan, whatever the case may be. the number of iterations you want to do, and then the functor that it was going to be called. And the work assigned is assigned to the argument by an index. So this index will call your functor from 0 to n minus 1 times on the hardware somewhere. One of the very important things is that there is no guarantee when this thing gets called what order it's going to be called in, because it may be called, if you have a loop which is 10,000 long and you've got actual 10,000 way concurrency on the GPU, they all happen at the same time, theoretically, modulo the hardware scheduling. Or if there's, you're doing 1,000,000 and only 10,000 threads, we might do it from back to front, we might do it front to back, we might start in the middle and execute in any way. So there's no guarantee of the ordering that these things get called in. So they truly have to be parallelizable kernels. So how do we pass the data into the computational bodies? So in this case, there was the loop before, and you had some variables that were going to be used. And so those variables have to appear. So the statement that you would show up here shows up here. And so these things actually have to be data members of the class. So Atom Forces is a data member of the class. That's a functor. So that's what a functor looks like. You've got some data members. You've got the operator that does the calculation, telling it which unit of work to perform. And then, so if you do, just so you can see that there's no magic involved, this loop, if you want to run it in serial using a functor, then you just run it and call a functor in serial. I mean, it's that simple. So complete picture using functors. So you write a functor, you put your loop body here, you call a parallel 4, it will call that functor with the index going in here. Okay, this has been the pattern for functors for C++ for decades, and people got really tired and really thought it was really tedious. So C++11 came along and said, this is really tiresome and tedious, we're going to quit doing that, we're going to just create lambdas. So lambda is simpler. Lambda, all we cared about in that was actually the body, the loop. I mean, the rest of it was just plumbing and machinery and tedium. So what the lambda does is now it will, you can put this calculation in. This is a lambda expression for C++11. Now we can do the parallel 4, number of atoms, lambda expression. Here's the argument that goes in the loop body that was there before. Well, there's no magic to this. All that stuff I showed you about the plumbing for the functors, that's just the compiler. It's such by rote that the compiler can do it for you. The compiler looks in this loop body and says, oh, okay, here's the variables you're using. I'm going to create an anonymous functor and behind the scenes and do all this tedious plumbing for you automatically. So the one wrinkle is that the capture. And this is how you telling the compiler, how do you want it to do that tedium for you? And so this is a capture by value. And so what capture by value means is that whatever variables are being passed in, they're going to be copied. Those variables are going to be copied. So Atom Forces, if it's a pointer on the outside, and it comes in, you copy the pointer, and away you go, and you're in great shape to run this thing. The important thing about using capture by value, and that to be able to make copies, is that in order for us to be able to take this lambda that's produced by the compiler and shove it down in the GPU and run it, we actually have to make a copy of everything because the GPU can't touch the CPU memory. So we have to be able to make a copy. So it's very important to make the copy. And then where that bites people on this is if they have existing data structures like std vector and they're using and they try and grab that by copy, you've just copied the entire vector and tried to shove it down in the GPU, and squirrely things happen. So there's going to be some, we'll get into that in a second unit, as to what do you use instead of your conventional C++ containers to be able to get performance portability across these devices. So how does it compare to OpenMP doing this? Serial loop, OpenMP, you decorate it, and in Kokkos, you just say parallel 4 and put your lambda there. And so if you look at it, we did some studies where you took an application or a mini application, did these kind of transformations, went from serial to OpenMP, went from serial to Kokkos, And it's pretty much a dead heat in terms of how many lines of code you have to touch to do the simple stuff. Once you start doing the hard stuff and you have to start stacking up a lot of OpenMP pragmas, Kokkos turns out to be a big win. Okay, so this is a thought exercise to, putting this all together in terms of pattern, policy, body, and then capturing by value, putting it all together. So let's just do the most trivial thing. Let's do a numerical integration on a trivial function. So we have a serial loop, and we say we're going to do the number of intervals. We're just going to do the integration rule and do a total integral, and at the end you get a total integral, and then, well, scale it by dx, so you don't have to worry about scaling every time inside the inner loop. So that's what it looks. So how do we make this thing parallel? Well, we got a pattern. We looked at the source code, and we saw a pattern, a body, and the policy. So just to let you know ahead of time, this is the wrong thing, but what's wrong? So if we do this, Kokkos parallel 4, capture by value so that we know we can pass it to the GPU, and the compiler is going to give you an error if you try to compile this code. Because you captured by value, that means this total integral thing is not the same as this total integral. It's a copy of it. And the compiler is actually going to tell you that, hey, you can't do that because you've made a copy, and that copy is a const copy because it's trying to protect you from doing silly things like this, and it won't work. So what do? Well, if you're in the mode of, well, if the compiler's not going to do what I want, then I'm going to force it to do what I want, and it's as opposed to stepping back and scratching your head for a moment, then you can say, I can trick the compiler. I'm just going to do a pointer. I'll take the address of it. I'll pass that thing in, and away we go. And it'll compile, it'll run, and you're going to get garbage. Well, why do you get garbage? Basics of parallel programming and shared memory. You get race conditions. Race conditions are very easy to introduce if you're not careful. So in this case, you could have two different threads which are going to be loading this variable out of a pointer, adding something to it, writing it back out, and you end up with these loads and writes and increments all conflicting with each other, and you'll end up with bad data. The root of the problem, if you stop and scratch your head instead of just powering through with a compiler, is that it's the wrong pattern. So pattern, if you look in source code, every pattern you see is a parallel 4, because everything, you get 4 everywhere, or a while, but 4 everywhere. The patterns when you get into parallelism are really important, which is why we've focused on patterns and policies. And the problem is that this isn't a parallel 4 pattern, this is a parallel reduce pattern that's been going on in here. And that is we're trying to combine the results of each unit of parallel work into some value. So it's a parallel reduce, not a parallel 4. So OpenMP's got the same thing. If you try to do it in OpenMP, you'd end up with the same kind of race condition. So in OpenMP, you decorate it with, this is by the way, the pattern is a reduction, and here's how we want the reduce to go. And then and the reduction and the operator you go, and things work out, and you get rid of your race condition. Well, in Kokkos, instead of saying parallel 4, because that was the wrong pattern, parallel reduce is the right pattern, you just say parallel reduce, functor, and then be able to pull that final result value out of it. Okay, so there's a little bit of a difference now. Just like over here, we had to say that, okay, this is our reduction variable, and so what's going to happen behind the scenes in OpenMP, when the compiler does the OpenMP, honors OpenMP directives, it actually doesn't take this variable, and this variable, actually different variables in the grand scheme of things. So it creates thread local, OpenMP compiler will create some thread local temporaries such that this is a private value, and then when the OpenMP loop gets done, it'll take that private values, put them back together, put them in the actual total integral loop here, and then you'll get your reduction. Well, we do the exact same thing because that's the thing that makes sense to do. Except, so what's different now is that instead of hiding the fact that, these are actually two different variables of the same name, which could lead to some confusion, we just say, okay, we'll just take and add another argument saying this is your private variable to update inside your function, And then when this whole operation finishes, we will make sure that we've added them up in a thread-safe fashion, in a thread-scalable fashion, into this variable that you passed in. So now we take the two arguments, the work index, what we need to update, and then that value gets reduced at the end. Okay, so you got a couple of tools in your pocket now. You can do a parallel for and reduce. They're pretty straightforward to do, especially if you can use the C++ 11 lambdas. Okay, so a naive thing that I would just want to head off is that there's sometimes a notion, until you've actually experienced it, that parallelism is kind of free. I say I want this loop to run 1,000 times, and it's going to be, if I have 64 threads, it'll be 64 times faster. And that's just, for OpenMP, it's not true. OpenACC, for Kokkos, it's just not true no matter which programming model. The problem is that when you're doing these things, when you launch parallel work, and this is a very simplistic performance model, but actually it holds up pretty well, that there is a latency just to getting things running in parallel. Just to get things started in parallel, there's some latency. And then you've got the time for a unit of work, the amount of work that's going to be done in parallel, and the amount of parallelism you actually have. And so the time you have is going to be, you'll be getting some speed up, but you got this kind of constant overhead just to get things moving in the first place, get the parallelism launched in the first place. And so the speed up that you actually get is going to be reduced by this latency times the number of threads. If you go through and do the algebra, you'll see it's a pretty straightforward thing. So you actually have this penalty over here. So you want this term to be very, very small, so you actually get the speed up for all the parallelism you have. So you want this to be small. All the runtimes, we all try to make this alpha, this latency overhead, as small as we can. They're constantly working on that. So if you're having problems getting speed up, can you find more parallelism? Can you increase n? Can you merge and fuse your loops to make beta bigger by putting multiple loops inside of a single launch to make this term here get bigger? And if you do the numerical integration example, we see that. I mean, it's a pretty simple thing. So we're old graph, so using K40s in the Knight's Corner as opposed to Knight's Landing, but the trends still hold. Alpha, your startup cost is dominating down here. This is speed up over serial. And then once you get enough intervals in there, because it's a trivial amount of work that's going on, just a few flops per iteration. So trivial amount of work, but once you get enough work in the system, then you are getting the parallelism you expect. So if your loop is too small or you don't have enough work, you're going to be sitting down here and you'll actually can see slowdowns as opposed to speed ups because that alpha term is just eating you up. Okay, so reoccurring exercise, come back tonight and we'll be doing this exercise, is this simple inner product, weighted inner product. So y dotted with ax. So we have A is an n by m matrix and using this exercise throughout. Okay, so if you're going to be doing the exercise tonight, it'd be a good idea to have downloaded this so you can have this up in another window while you're doing your actual exercises. So we have the Kokkos include. We do some necessary setup, and one of the important things is if you're doing one of these hybrid MPI Kokkos underneath or the multi-level MPI plus X, they call it, parallelism, you initialize MPI first, and then initialize Kokkos, do all the computations in the body, call your functions, call whatever, and then finalize Kokkos, and well, finalize OpenMP would be going in here as well. And you can set, on the command line, you can set various arguments for the parallelism. So the important thing, I guess, to note here is that if you're doing this MPI plus X, the MPI initialize will often take arguments that were passed to it by when the MPI processes were started to bind it to cores, like do I bind it to a NUMA region, do I bind it to a socket, those kinds of things. And then Kokkos, we honor whatever the MPI initialize set. We'll honor that when we do the parallelism inside. Okay, so in this exercise, first exercise was going through and getting this to go introduce the parallel for, parallel reduce to get it to run in parallel on a CPU. And then we get the performance looking like, at least on the old nice corner, it's gotten better with nice landing, and the Haswell. This is doing varying the number of rows and number of columns in the matrix, keeping the matrix size fixed, but just making it, taller, skinnier, or fatter and shorter, to where if you don't have enough parallel work, the alpha is eating you up. Once you can get up and get enough parallel work, then you get a very nice speed. So we measured on this one bandwidth, since it is a bandwidth limited problem. Okay, so there's some things you can do that I didn't mention in here. Parallel so far is that this parallel reduce, and the example in the tutorial, an example I gave earlier was just parallel reducing over a double precision number, and that can actually be tailored. You can tailor it and have different data types. You can have different reduction operators like min, max, etc. So I did the parallel for, parallel reduce pattern, parallel scan pattern for doing exclusive or inclusive prefix sums is another pattern that can go into that's parallel. And then a tag dispatch mechanism. So where this comes in is for small, simple things, those lambda expressions are very useful because you can put, a few tens of lines of code and be able to make it go parallel and to be able to do a transformation. A lot of our applications will have classes, like a class which is the CFD class. And inside of that class, there's different computations that are applied. And so those computations are members of the class. So we have one class that we want to be able to do multiple parallel, to be able to plug into multiple parallel iterations. And there's a mechanism for doing that to be able to say, oh, I've got multiple operators that I want to parallelize inside of a class. So we didn't do that. So hope you saw at least the convincing thing is if you've done the exercise. It is simple to use as OpenMP. Advanced features are incrementally straightforward. Beyond that, data parallel patterns, keeping in mind the pattern, policy, and body, and that the user provides computational bodies as a functor or a lambda and be able to plug them in. Okay, a view. So I mentioned before that to get portability to these GPUs and such, you can't use your vectors, you can't use your stood vectors, your stood maps, your stood sets, your other standard containers, because they have container semantics, and things will copy in ways that you don't want them to copy as you work on these systems. So motivation for a view, and this goes back to our earlier example. So say we have our lambda expression, and we're going to be doing a simple AXB operation. So y, ax plus y. So to do this, we have the pointer. We're going to operate on it. If you do it as a functor, then you have to capture the variables and do it. If you do it as a lambda, all those problems are going to do. Now the problem on this is if you've done this new double, that means x and y reside in CPU memory. That means the GPU can't touch it. So what do we do about that? How do we handle that properly? So we need a way of storing data. And in Kokkos, data is a multidimensional array, being that we come from a computational background where we need actual multidimensional arrays, not one-dimensional arrays. Storing data, multidimensional arrays, and then being able to decide where to put that data and how that data is going to be managed. So a view is a very lightweight class. So we get in, you'll see Kokkos : view in those tutorial examples. It's a lightweight C++ class that has inside of it, it's got a pointer to the array data and a little bit of metadata that goes along with it. So we template it on the data type, and then there's some other template arguments that I'll get into later. So we can template on the data type and say, okay, now I've got a double precision, and this is telling it's a rank 1 dynamically sized view. I'll get into details as to how you see that. And then we do a parallel for, you can carry those things through and capture the view, which is just a pointer underneath, and a little bit of metadata, capture that, pull it into the lambda, and be able to execute it. So views are like pointers. You can copy them just as if they were pointers. They're just as safe to copy around. You're copying around the pointer to this big piece of data. You're not copying around the big piece of data itself. So a view is a multidimensional array of rank 0 or more. Well, a scalar is a rank 0 multidimensional array. A vector is a rank 1, matrix rank 2, and then you go on up and start getting into tensors. The number of dimensions, or the rank, is chosen at compile time. Arrays are always Cartesian products of their index spaces. They're not ragged arrays, so it's always n by m by k by whatever the case may be. And then the size of the dimensions, the actual dimensions, the length, they can be compile time or runtime, and that becomes important for performance. So just some examples. So this is a view which is a three-dimensional array where you have 3 dimensions that are going to be provided at compile time as opposed to runtime. I'm sorry, reverse. At runtime as opposed to compile time. So you give them as arguments, you construct this thing, you give it a label. The only thing that's used for is error messages, like if you do an array bounds violation, it'll tell you instead of saying at address blah, you did this, it says no, you violated label at in the multidimensional indexing range for that. So this is 3 runtime dimensions, 0 compile time. Down here we have 1 runtime, a couple of compile time dimensions, and so you give the runtime dimension here, or everything is done at compile time. And the motivation for this is when if you can ever have, the more information you can provide at compile time, the better job an optimizer can do with doing the indexing calculations into the array. So if you know something is always going to be 3 dimensions, like you're going to have a matrix of XYZ entries, then you have the 3 here, and the compiler can at least optimize out part of the indexing calculation. Okay, so a view, allocations of the view of the underlying memory that the view is looking at, they only happen when you explicitly specify that you want this to be allocated. So one of the ground rules I put in place early on in this project is we are never going to hide a memory allocation from you. If you're going to allocate a 10 megabyte array, you're going to see it. We're not going to put some hidden buffer behind the scenes and allocate it and chew up your memory without you knowing it. Copy construction and assignment are shallow. So if you say one view equal another view, that's just saying one pointer equal another pointer for all intents and purposes. So you can pass views by value. You can capture them in your Lambda by value and safely pass them down to a GPU, and everything works fine. And if you're familiar with the C++11 shared putter, they behave the same way. Okay, so what I mean about shared putter, that means shared ownership semantics. If you're familiar with those, okay, I'm going to find out, see if people seem to be awake. I'm going to do a pop quiz here. So we have views, like what does it mean to have shared putter or shared ownership semantics? So we have view here, one-dimensional array, A and B. So this guy, they both get allocated at this point because we said, okay, allocate during construction. And then we assign A equals B. Okay, so now we have, remember I mentioned before, it's like assigning pointers, something like that. So then we have another view which gets constructed, C, but this is now a copy construction of B. So then we go through and assign things. So just to trigger a hint, aliasing. So if we say, set A, set the 0th element A, set the 0th element B, set the 0th element of C, and we say print A. What gets printed? All right, I heard some 3s, so we got at least some people who are familiar with aliasing and shared semantics. So yes, because what happened, we allocated 2 arrays. This just said A is, we set A to what the contents of B are. That means A actually got deallocated right there. Remember I said I wasn't going to allocate anything behind the scenes from you, but I will deallocate. So B got, whatever was in originally A, now got deallocated. And the reason it got deallocated because you no longer have anything that's looking at that memory And if there's nothing looking, if there's no pointer to that memory, there's no reason to keep it around. So I did hide the deallocation, but not the allocation. Allocated something else. Well, we didn't do an allocation here. We just did another alias. So now we've aliased 3 things together. There's only one allocation behind the scenes, which is why all that happened. So this is really important to, when dealing with these views and allocation, to be familiar with how these things behave. Okay. Well, if we were doing exercises, it would be time to reinforce that learning with an exercise. And this would be taking that example. And so I'm hoping I'm teasing you to come back, at least some of you to come back tonight and try this out. Come back and compile. We take that same code. We're going to do a little flips on the compile line and activate it on the GPU, just making a few modifications to do views so that we can handle memory and memory placement, and things will run on the GPU. Okay, so things which we're going to cover in just a minute here. What a memory space is, and then so how do you control, as opposed to just letting things, so when we do this example tonight, exercise 2, we're just setting up a bunch of defaults when we build the thing, as opposed to letting things default, keeping it very, very simple to look at, and by using defaults, now we're going to be getting into how do you explicitly control where the view is data, where data is going to reside. Okay, well I said these were shallow copies. If you say A equal B, now you've just got two pointers to the same memory. So actually, if we don't want to make 2 pointers to the same memory, you actually want to copy things over, copy the big bulk of the content over. How do we do that? Layout, memory traits, and subviews. Unfortunately, we're not going to be able to get to subviews, and that is if you have a multidimensional array and you want to get a submatrix within a matrix. That's what we call subviews, and being able to have a view which looks into a subset of another view as opposed to looking into the whole view. So, execution of memory spaces. So we have heterogeneous nodes, and that first illustration I gave, yeah, I didn't repeat that slide this time. So we have heterogeneous nodes, different kinds of cores, different kinds of memory, lots of different kinds. It's not a one-to-one thing. You could have many more kinds of memories than you've got things to execute on. And so how do you control where that data lives if you want to start managing, saying, okay, I want some things to work on the CPU, some things to work on the GPU. How do I coordinate and decide what goes where? So that's how you control it. How to avoid illegal memory accesses. Basically, how do you avoid a core of some flavor touching memory of some flavor that it doesn't have a permission or doesn't even have a wire to touch, doesn't have a direct route? How do you control that and manage that? And a little more details on the Kokkos finalize. And then what we have to do for annotating things to make them run in parallel. Okay, so a little thought experiment. So we have 2 pieces of code here. This one, well, this one, we'll start with this one, section 2. It is inside of a Kokkos pattern. This one is outside of a Kokkos pattern. Okay? Given that hint, where does this code run? Oh, come on. Was it? Yes, thank you. Okay. Okay. Now, where does this code run? It depends. GPU. If you want it to run on the GPU, you can make it run on the GPU. If you don't want it to run on the GPU, you can make it not run on the GPU. So yes, it depends. Now, the important thing is, how do I control this thing? That we control that thing by what we call execution spaces. Okay, execution spaces. For in our theoretical architecture here, we've got 2 execution spaces that can actually have further partitioning inside of it. We've got the CPU execution spaces, and we have the GPU execution spaces. So we kind of blend a little bit more than just where the code runs. It's actually an execution, the place it needs to run, and what is the primitive underlying mechanism by which we can get something to run on it. For example, execution space example, a serial threads execution space means I'm going to use P threads to run on the core. OpenMP execution space means I'm going to use OpenMP constructs to run on that core. CUDA execution space means I'm going to run on a GPU using CUDA to run on a GPU. So it's the primitive mechanism where I'm going to run and what is the primitive mechanism for to make things work on that, So in this case, where will the host code run? It'll always run in the host process. And where the parallel code in this case, it'll run in the default execution space unless we say something else. So there's always a notion of a default as to where you want this thing to go unless you tell me otherwise. So how do I tell you otherwise? How do you tell me otherwise? So where the body is executed. So we can either change the default execution space. So that means we can go back and recompile the code with a different line, compile line option, or we can specify it as part of the policy. Okay? So this is the difference. So before, we just said number of intervals was the policy. Well, that policy had a whole lot of defaults that were going on to it. The first thing is we said, okay, if you just give me an integer, that means you actually meet what you really want is a range policy that goes from 0 to the number of intervals minus 1. So this is the default. But if you do it explicitly, you say, I want it to go range policy going from 0 to number of intervals minus 1. Well, if you do a full-blown policy, which is a little more long-winded than just sticking an integer in there, you could actually specify where you want it to execute, what execution space, and you could actually give it some different rate, going from 2 different numbers instead of going from 0 to the normal thing. Okay, so some requirements for being able to use these execution spaces. Well, first of all, when you compile the code, you've got to set flags that say, oh, I do have a GPU attached, and I do want to be able to run on it, or I do have OpenMP available in my compiler, and I do want to run on it, or actually I have put the -LP threads on the link line, so I can run on a pthreads backend. The execution space has got to be initialized or finalized, just to do the setup to be able to run things on whatever the particular backend is. Now the fun part, and this is one of the annoying things, but we're going to have to live with it for the foreseeable future, is that functions and lambdas are going to have to be marked with a macro such that they would be able to be run on the GPU. So if anyone's ever written CUDA before, just out of curiosity, how many have actually done? Okay, good. We've got probably about half of you, it looks like, have messed with CUDA. And you know how annoying it because it is when you have to do the mark with the host device everything. We're stuck with that for the foreseeable future. So what do we do about that to deal with the portability so that we don't have to sit there and mark and unmark and mark and unmark? Well, if you've done any kind of C or C++, you do macros. And so what happens is you have this, we've created this macro. It's a Kokkos inline function that we annotate functions with. And if you have activated CUDA, then this is what the macro turns into. But if CUDA is not activated, then it just disappears. So if you mark your function and detects whether the compilers happen, whether the compiler is CUDA compiler or not a CUDA compiler, and then it just marks things as appropriate. So a bit of a nuisance, but once you start cutting and pasting and just do your yanks and puts on with your editor, it's not bad. So, yeah.
Can you guys handle the separable compilation model and like with your CUDA code, like say you have like a traditional header file and then your class implementation?
With CUDA 8 and better, yes. With anything older, there was a bug in the CUDA linker and it didn't work. Even though they said it worked, it didn't. So yes, and so instead of and actually when that one, so since you braided up, there's another macro called Kokkos function instead of Kokkos inline function for doing that separate compilation. But then you have to have CUDA 8 or better, and you have to have the CUDA relocatable device code option set when you compile to be able to do that. Okay, and then Lambda, the Kokkos Lambda is similar. And since CUDA 8 came out, this annotation changed from device to host device. Before CUDA 8, which is when these slides were made, it was just device. So, but now since we control the macros, we can say, oh, you're running CUDA 8 instead of CUDA 7.5, and I'll inject the right macro. You don't have to go back and edit all your code. We'll just inject the right macros as CUDA or whatever else evolves. So, handy to do that. Okay, so memory space. Let's do a little example here. So we have a view, we've done an allocation to a particular size. Going to be going into some memory space, and now we're going to do a range policy, and we're going to do a summation. We're going to do a parallel reduce and just sum up the contents. We'll just do a straight summation of the contents. Okay, so we talked about where things get run, but now there's about where things get stored. So this data stored. So when we say this data is going to get allocated, does it get stored GPU memory, CPU memory, both? I won't do the pop quiz right now. So we have two different accesses here. Let's say in this case we're going to read stuff from a file and stuff it into data. You notice this is outside of a Kokkos parallel whatever, so it's going to happen on the CPU. This is inside of a Kokkos parallel whatever, so it's going to happen in some example execution space. But how do we control where that, so this is how we control where the code is going to run, but how do we control where the memory is going to be? Instead of execution spaces, it's memory spaces is how we control that. So memory space. Lots of different kinds of memory are possible, and the situation is getting more interesting by the year. So we have the high bandwidth memory that's sitting there on package, the DRAM sitting out there. There's a lot of discussion about sitting NVRAM out there. Go to the accelerator, we have on-package memory, and then we also have the shared memory inside of the accelerator cores themselves. So we have a lot of different memory spaces. But basically, a memory space is, where do I put the data? Okay. So every view is stored in memory space that is chosen when you compile the code. Okay, I wasn't sure if it was a question. Okay, never mind, not a question. So in this case, I said there were some other template arguments. Well, here's one of the other template arguments. And one of the other template arguments is what space do I want that data to live in? So we have host space, CPU, CUDA space, the CUDA UVM, because we got the unified virtual memory on CUDA, which is actually different if you do a CUDA malloc versus the CUDA malloc managed, a different thing entirely, and more spaces that go. So similar to the execution space, the memory space is not just physical memory, but how does the underlying embedded runtime of CUDA or whatever, how does it actually manage access to that? So UVM is both a physical thing and a access mechanism which is buried down inside the kernel and down inside the driver. So also it turns out, to try and keep things as simple as we can, that every execution space has a default or a preferred, or this execution space likes this memory space the best, so that's the default for it. And so this space can either be a memory space or an execution space. If you pass in an execution space, it says, you intend to use this view in that execution space, and you didn't tell me which memory in particular, so I'm going to pick the memory that the execution space likes best. And I'll just use that. So that's why these views will take any kind of space. So if you don't provide a memory space at all, you just say the view double in the first two exercises, that's what happened, and truncate it or stop the template right there, then what happens is that there is a default execution space that you specified when you built the code. And since every execution space has a memory space that it likes best, then that default execution space, memory space, is what is used for the default place to go put data. Okay. Well, now we put together views. We put together these memory spaces, we put together functors or lambda closures, the lambdas, whatever, and things start getting interesting because now we've got this combination of things going on. And it's really important, and it'll save you a lot of heartache if you just get a few concepts and get this notion rolling as to how to handle that and what's going on. So we'll take this example. So we've done a view. Remember, the view I said was the pointer and a little bit of metadata. The actual little bit of metadata is the dimensions of the array. So a pointer and a few integers. So when you do a view in host space, we got this little tiny little view data object and some allocated memory that sits there in host space, depending on how big you say to do it. So, a few words, could be megabytes. And then if you do CUDA space, so if you put this view statement in your host code, and you say I want to allocate in CUDA space, then you've got this view object, that view object, which is a few words, sitting there in the host memory, and then the memory that's been allocated is over there in the GPU memory. So we have where does the metadata live and where does the actual allocated, big chunk of data live. Very important to keep these straight as to which one is where and when. Okay, so here's the when, and to get some intuition going so you don't have problems later. If you get a little bit of intuition, it becomes habitual. So let's see if we can jumpstart you on this intuition. So anatomy of a kernel launch. So we declare some views. Like say in this one we declared we wanted to live in the CUDA execution space. Well, not really the CUDA execution space. The memory space that the CUDA execution space likes best is where this thing gets allocated. And then the user creates a functor with the views, or it does a lambda. And then that lambda that will capture the this view. And remember that when it captures making a copy, we're making a copy of a pointer. So all we do is take those few words and we copy it into the functor, which the compiler automatically generates because we did capture by value. Then this functor, the parallel 4, if it's going to be running on let's say in this case the CUDA was the default execution space, it will copy the body of that lambda. It'll take that, it'll copy it down to the GPU and run it. And then the copy of the functor, once it's finished running, the copy of the functor evaporates from the GPU. So there's no deep copies of the array data. The only thing we're copying basically is we've copied the view metadata, those few words, into the closure. I'll start using the proper lingo, into the closure that's defined by the lambda. Then we take that whole lambda and we copy it down to the GPU, so it's a few more words. So you're looking, not more than a few hundred words, even for some of the bigger and more complicated lambdas that get captured and shoved down. So let's walk through it very carefully. So in this case, device gets allocated there, create the closure. We copied that closure. When we took this closure that was created by the lambda, we copied it over to the device, and then we ran something. Okay, now let's say we have two different views that have been allocated two different ways. So we have a CUDA view, which is allocated over here, the CUDA's preferred memory space, which is on the GPU. The host memory space over here. Now we'd make a copy of the metadata associated with these things. Let's assume an allocation occurred, truncated from the slide. Then these things got captured. The metadata got captured. The metadata got copied. We tried to execute something, and that will give you a fault. And you'll get a runtime error out of it because you passed something in, you get a runtime error out. Not good. Okay, so we have the view now. Now we go back to this original example. So we want to go back and say we're going to load something up on the host, and then we're going to actually process it on the device because we're going to be doing a range policy on CUDA. CUDA memory space, CUDA execution space, and try and do this. Well, now we get a fault because this was allocated in CUDA memory. Host can't touch CUDA memory, doesn't have any channel to do it, so you get a problem, you get a fault. Okay, so, oops, okay, we want to load the data into something we've allocated on the host, so we change that to host, we load the array, now we go to execute, fault. because now we're trying to touch the data that's been allocated on the host on the GPU. This is where it starts coming in, where you got to be taking care of this thing. So what do you do about this if you want to access data sometimes on the CPU and sometimes on the GPU? Well, one thing that, since this was a pervasive headache for people, especially that are the more naive users, NVIDIA invested quite a bit of time and energy into creating this unified virtual memory. And that's where it actually uses some pretty impressive machinery in their drivers to be able to intercept page faults and actually migrate pages back and forth between the CPU and the GPU. It is really nifty, really handy, very, very nice to use. The problem is, under a lot of circumstances, under many circumstances, you pay for that convenience with some nasty performance loss because you're migrating pages back and forth on demand. Another thing you could do is there's this thing called the CUDA host pin space, which is another thing in the driver where you can pull pages off the host and bring them down onto the GPU. Once again, that's a way for the GPU to be able to access host memory through drivers which do page faults, pull things down. Slow. Convenient, slow. So the one that's not slow is what we call the mirroring technique. Okay, well, so what I mentioned here, if you do UVM, what actually happens is we don't do this. The Kokkos doesn't do this. The CUDA driver does this. And that is you have, if you say UVM space, and actually the driver will do two allocations. When you say, allocate me a UVM, does two allocations, and it will do page faulting to make sure these things go back and forth. And you get a performance hit. One of the problems, if you try and concurrently access from the CPU and from the GPU, all sorts of nasty things happen because it can't keep up with which one is the right one to be accessing. So it's what I call the training wheels, and just because of it will cause later problems, you want to take those training wheels off as soon as you can learn how to. So mirrors. So what we want to do, this is Kokkos' way of doing what UVM intended to help you with, but making it much more explicit so you have a lot better control over what's going on and a lot better understanding of when things happen. So what we want to do is have equivalent arrays residing in different memory spaces, a mirror of an array. So now what we do is we have a host view in some space, and that gives you, you can do a type def or using if you're gotten more modern. Now what we do is this view type has a type inside of it called a host mirror. And what that means is I want the exact same array that I gave you here, except for I want it in host memory space. I want same shape, same dimension, same rank, same everything, even same name, but I want it in the host space. And so then we can go through and we can say create mirror view. And so what happens is we have the view, the original view, pointing over here, the host mirror, the metadata, this metadata. It points to an exact image of what was over here in terms of shape and everything else that went into that. Okay, so create a views array in some memory space, create a host view to get that, we call it a create mirror view. So now we can populate the data we can populate this host view on the host. We can read it from a file, whatever the case may be. And then now we want to copy the actual content of that multi-megabyte array. We actually want to copy that content from the CPU into the GPU. Well, we said that just assigning the things A equal B is a shallow copy. Copying deeply is a deep copy. So now it says copy the content of this thing that was allocated from here to here. And now it will go through, and instead of doing this page faulting mechanism and all that, it will do the absolute best mechanism can be done with basically the CUDA mem copy where it streams through as best it can. And then there's also a variant where this can actually be asynchronous so you don't lose that capability. Now we can launch a kernel, which runs on the space, using the view, use it and change it, modify it, run as many multiple kernels, and in the end, you copy it back just by reversing the arguments. You say, I want to copy from here back to here. Now you can output the result. So we explicitly manage, so we're not hiding any allocations. You allocated it when you said create me a mirror view. You allocated that in your code. Okay. Well, then the first thing that comes up, well, that's well and good for when I'm running on a GPU, but what if I'm just running on the CPU and I'm just using OpenMP or whatever it is for the backend pthreads OpenMP? Now I've created 2 copies. I'm thinking there was no good reason to have created 2 copies other than the programming model forced me to. Well, we don't want to do that. We don't want to lose performance just for the programming model. So what we do is, in this case, if the original view is in the host space, then it does not allocate data. All it does is, since they're the same shape and everything is the same except this one's host space, well, if the one you originally gave it was host space, then they're identical. And if they're identical, then we can actually just make them alias the same memory. So what will happen is create mirror view. We'll look at the space of this one, the space of this one. If they're the same space, host space, it'll just give you back a pointer. So now you've got 2 references of the same data. And then what happens is the deep copy then says, hey, you're trying to deep copy from the same thing, so I've just paid the overhead of this pointer equal that pointer, return. So, which is not much overhead. Okay.
I'm sorry, but I don't see the history of this. So basically, what's the difference between having just a view, a normal view, and providing the functionality to actually transfer the data? Because your point is that if you rely on like pin memory, like with CUDA, like a unified memory, then you pay the cost of paging. While in this case you provide an explicit model, then why do I need to declare it mirror in that regard? Can I just, I can use my host memory, right, and then call that function. Wouldn't that be more simple? I'm sorry,
It is, and that's what we say when people get started to put the training wheels on and use UVM. But the problem is that...
In your case, you're differentiating between 2 types of view. One, you have like a mirror of like a normal
That's
view.
just a term we picked anyway.
Yeah, but wouldn't it be more simple just to copy? I can say like, oh, this is on the host, I just copy to the GPU. Why do I need to do this step of mirror? This is what I'm trying to understand. What's the difference?
Because so if you want to be able to access this data, and that data lived on the GPU, you just physically can't touch it on the CPU. So you need to have a copy of it on the CPU.
Yeah, but still the model is explicit, right? I need to call some kind of like CUDA CPI with your syntax.
Yes, the deep copy under the covers calls, if it's CUDA, it calls CUDA mem copy. If it's not CUDA and it's just host space, it just says, nope, I don't need to do anything. So, yeah.
The key here is that if you're not pushing it to a CPU, it has a fallback position. So if you only are on our GPU, if you're only on the CPU, when you mirror it, it doesn't do anything.
Right.
So that's.
But that's like if I do a mem CP, like a mem copy.
But
right?
you're not going to do a mem copy.
Yeah, but I do a mem copy on 2 addresses, and it should return and say, oh, it's the same address.
Well, you've
right.
just allocated it.
So this is where we've got about 15 minutes left. And the conversation's taking longer, so let's get together this evening,
I'm sorry for
and we'll go into the details.
I'm sorry.
Okay. Well, that's good to ask questions. We just need, in the interest of time, short questions. Okay. So exercise 3, go through this process. So on exercise 3, we take the training wheels off, we quit using UVM, and we make sure everything works out nicely, and away we go. Okay. So a view essentially is a pointer, smart pointer, a shared ownership pointer, whatever you call this thing, to multidimensional data. residing in a memory space in which you can specify what memory space that is. It abstracts away some platform-dependent allocation. So instead of calling, you just say, allocate this view, and based on what space it is, it knows what to do in terms of allocation, deallocation functions. Lots of different memory spaces. Mirroring to be able to get performant access between the host and device, so we can do streaming copies between the two as opposed to these page-faulted copies. And you've got full control over where you want to do this if you want to, instead of using the defaults, and you can explicitly specify these things. And that happens in the exercise. Okay. Managing memory access patterns. So I started off by saying that, okay, everything so far is addressing portability, accessibility, getting things to actually run. Now running well is another matter. Now we get into the importance of layout. How is a multidimensional array laid out in memory, and why is it so important, and how do you take care of that? So in this example, we do a parallel 4, and then we have inside this parallel 4 parallel reduce because we're doing that dot product example. And inside that parallel 4, we run across these rows doing the dot products as an inner loop. And so accessing A as a matrix, rows and entries across in this matrix as we go. And so the driving question is, how should A be organized in memory? It's pretty obvious for the one-dimensional. It's just put them contiguous. But how should A be done? Should it be done row major column major the way Fortran does it, row major the way C does it? What's the best way to do it? In the interest of time, I'm not going to bait the discussion right now. So at a column major, basically it's contiguous. We get to the bottom of the array, we jump back up, bottom and jump back up, and you do that. Row major, you do it this way. So equally valid in terms of correctness. It's one in terms of the storage, one as good as the other if you're just considering storage only. So every view has a multidimensional layout. So it's another template argument that goes in. And once again, if you don't put one in, it defaults. And what does it default to? It goes back to what space you're going to put it in. And from what space you're going to put in, what's the favored layout for that space? Default, default, default. Okay, so layout left, we call them layout left and layout right since it can be higher than a matrix. So basically you start at the left and you stride rapidly, and then you increase the stride as you go out. Layout right, you start on the right, increase the strides as you move, and then it defaults. So these can be extended. We've done some, there's a layout stride. There's a prototype layout for doing tile layouts, if you're familiar with tile layouts. And we have an exercise in which you go and experiment with what impact, so you see for yourself what performance impact changing the layout does in that trivial example that we did. And so, what difference it makes. So these are different architectures. Architectures are old. We haven't had a chance to go and rerun all this stuff for the new architectures. But anyway, we did get this one done for Knight's Landing at least, but still the K40 instead of the P100. So the only difference between these things is we change the layout and ran it on different architectures. And so if we look at the K and L and this algorithm using a layout right, so this is basically how quickly we're able to stride through that array. So we're up here in the 300 to 350 gigabyte per second range with the K and L with a layout right. Wait, okay, here it is. Do a layout left. We're all the way down here. The exact same code. The only thing we touched was going to that template parameter and saying left and right. Same thing with the Titan GPU, except this one was a layout left on the GPU. This one was a layout right on the CPU. And we're up there running running out on what could be done. And we do the wrong layout, and we're all the way down here. It makes even this silly little example with the weighted dot product, it makes a huge difference on performance. So what the heck is going on here? Okay. I'm looking at time here. So thread independence. So what is going on here? So when we run this parallel reduce, then we're going to be mapping data onto the CPU. When we map data on the CPU, how do we want these things to interact? So CPU threads are pretty much, you get into hyperthreads on the Knight's corner type things, they're not totally independent, but for the most part they are. GPU threads are a whole nother matter. They work kind of in lockstep groups of 32. The Volta relaxes this, but for performance, it's still best performance is running in lockstep. So that means they run in a warp. So we have to look at caching behavior, CPU behavior, and we'll go, okay. So CPU, the way we want these things to be laid out is thread 0, we want them to be running through contiguous chunks. So thread 0 gets one big section of the array to run on, thread 1 gets the next section, thread 2 the next section, thread 3 the next section, as we go. So that way thread 0 loads a cache line, gets to use all of it. Thread 1 loads its cache line, gets to use all of it, and just imagine a ... so you've got some separation here. So GPU is a different matter. You want on a GPU, since they're working in lockstep together, you actually want thread 0, and let's say we have a 4 wide warp for the sake of argument. We want the 4 wide warp to be working on adjacent locations to be able to get the proper memory access pattern. So this is the caching notion, and that is if thread T, thread 1, works on a current position I, then we want the very next access instruction to be at I plus 1. So we can reuse that cache line that it worked so hard to get down from the memory into its core. Coalescing, and this is on the GPU, if thread T is accessing position I, then we want T plus 1 to access I plus 1. So it's transposed, temporally and spatially transposed from each other. And if you don't do it right, we saw the graph. If you don't get those things right, then you're going to lose performance and lose it bad. Okay. So when we map indices, so remember, now we're going back to the very beginning here. So we're going to map this range 0 to size minus 1, and we're going to map and call this thing from a particular thread at a particular time, space-time. So for cached, for OpenMP, and what we want, I'm going to start giving answers here instead of querying. What we want is that we want this behavior to be cached for OpenMP, and we want this behavior to be coalesced for CUDA on the GPU. So we want different spatial and temporal mappings depending on what architecture that you're sitting on. So we want this to be the behavior for the given P threads. We want a CPU thread to do this. We want a GPU thread to do that. And why do we do this? So when you go through the exercises. So this is what we call caching and coalescing, the vocabulary terms. So when we map this, when we do this, the parallel 4 on the range policy, we'll take and we'll map contiguous chunks of that range onto CPU threads, and we'll take the range and we'll stride it out across GPU threads. So completely transposed how those things get mapped onto cores depending on the underlying architecture. But notice that transpose, you never see it in the code. It all happens inside of the Kokkos launch, depending on what space you're going to be running on. So that's how we get portability, because Kokkos controls how your computational kernel, given your range, gets mapped onto the underlying hardware and does it in the proper way. Okay. So as a rule of thumb, so what we assume, since data structures are multidimensional arrays for our computations, what we assume is that the first index of your multidimensional array is the parallel work index. So we assume that this index, so when you decide what your dimensions are, the assumption we make when we default all of these things, to make things simple, we default lots of stuff, is we assume that in a multidimensional array, the first index of a multidimensional array is the parallel work index. So now we can so if you have mapped your data, if you've done your right indices, Now when we want to do when we go to do the CPU and we're going to be doing this algorithm, we can run this way and run this way, and we'll get on a host space, if we laid out this way, the host space, good cache behavior, because one thread is doing this, one thread is putting those things together. On the GPU, it's really bad. And if we do a layout left, we go into CUDA space, very good, because thread 0, thread 1, thread 2, thread 3. So we're doing a good job there. But then for the host space, it's terrible. And then so what we want is, if you're in the host space, we want to do one way. If we're in the GPU space, we want to do a different way. And that's what we actually do. And we will actually go through and say, this was allocated in GPU space. You allocated a multidimensional array in GPU space, we're going to do this layout. You allocated a multidimensional array in host space, we're going to do this layout by default. Now you can always override that at any point just by saying, no, no, no. I know better. I want my data laid out this way. Don't you default it on me. And so this is cached behavior on the CPU, coalesced behavior on the GPU, and just depending on what architecture and what kind of memory it has, but uncached, uncoalesced sits there at the very bottom. So it is really, really important to control and understand and control and have the mechanisms to easily control how your data is laid out. So if you're familiar with this array of struct versus structive arrays, all you do is change one template parameter and you've just flipped the data structure throughout your entire code without having to go back and edit anything except that one line. Or if you're satisfied with the defaults, you don't have to edit anything. Okay, so every view has a layout. That layout will default if you don't tell it. We do a default which will be nicely behaved if your first index is the parallel index on whatever architecture you're doing. These layouts are extensible, flexible. There's different layouts. Tiling layout is one of the ones we're working on layout next year to go from a kind of experimental prototype to something that we put actually in an application. It's a grid-based application. They want to be able to do stencil tiling to get good memory motion. So we want caching on the CPU, coalescing on the GPU. You control that by your layouts. And then we map parallel work indices and multidimensional array layouts. Mapping of work indices, mapping of the data, bring those together in a coherent fashion, and we get performance. We get performance portability, not just portability across these architectures. And one of the problems is when you start looking at these layouts and being able to control layouts and control mapping together, you don't have anything in OpenMP, OpenACC, OpenCL, which will allow you to just make that one change and flip your data structures in your code when you go to a new architecture. It just isn't there. It should be. We're telling them it should be. But how do you do it? With using just pragmas, that's an issue. So things we didn't cover today. So atomics. If you go and look at those supercomputing talks, we talked a lot about atomics and when you can use them. When you start getting beyond the very simple stuff with parallel form, parallel reduce, you need atomics, and you need a little bit of intuition as to when you can use them effectively and performantly and when you can't. So we have a new multi-dimensional range policy. That's when you have tightly nested loops, and how do you want those things parallelized, and how do you basically, like the pragma OpenMP collapse clause, and how do you do that in a purportable way once again. A DAG of another pattern, which is being rolled out. It's now in the baseline code to be able to do a dynamic directed acyclic graph, heterogeneous tasks, and then plugging in layouts. We can talk about that. Okay, so if you want portability, you can go to your pragma-based stuff, your OpenCLs, or you can go to Kokkos. If you want performance portability, you're going to need something more than what these guys are going to give you. That's why we wrote Kokkos. That's why it's being spread across the DOE complex. We've got some NASA applications and some DoD applications which are starting to pick it up. If you're familiar with UNTA from the Utah group, they've picked it up and they're embedding. And a whole nother unit on advanced performance advanced patterns, hierarchical parallel patterns in addition to these task-based patterns. Okay, we're at 0, and I'm on the last slide. Not sure what your control is for questions and all that as you transition. We got 5 minutes? Okay, we got 5 minutes, yeah.
Are there already any libraries, like for example for FFTs, that are based or using Kokkos and could be used in user applications?
So Sandia's Trilinos library is slowly working its way into converting over to be able to use Kokkos so that all capabilities in Trilinos will become hybrid parallel as opposed to MPI will be MPI plus Kokkos. There's another project that started called Kokkos kernels, which is just getting some fundamental, not MPI, but only on node parallelism for like sparse matrix vector multiply, sparse matrix matrix multiply, and starting some of these fundamental kernels. So yes, if you go to Trilinos, it's a growing set that are Kokkos enabled. And so there's libraries that are migrating.
In the process.
In the process, various libraries have made more progress than others, just depending on how much project funding they have to make those transitions.
Sorry. So how much control do you have over things like asynchronous data transfer between the host and the GPU, or execution of the kernel, or of code on the GPUs?
Okay, so for the asynchronous data transfer, that is a asynchronous deep copy. And so we have a version of a deep copy I didn't show here, in which you take and you say, for which execution space do you want it to be synchronized with respect to the host, or do you want it to be synchronized with respect to the GPU? So you can get the overlapping. And then you can stack those together with kernels so that you can asynchronously transfer and then launch a kernel as soon as that transfer is done.
I imagine you have the same controls with different streams. Can you do that?
So that is work that's in progress. For the stream side, that work is in progress. It's actually one of the people in the UNTOG group that's doing it for us.
Okay. And how much fine control do you have over like cache use, different cache uses on the GPU?
So that was another, and so for the hierarchical parallelism, we didn't get into team parallelism. We want to be able to do anything you could do in CUDA with grid block programming and using shared memory. And so we've had comments from people that have started using Kokkos thread teams instead of CUDA grid blocks. And the comment was, hey, I can do the same stuff and it's so much easier. so yes, I saw that.
How do you compare Kokkos to Raja? What do you think it does better and what do you think it does not as well?
You want to get me in trouble since I'm on tape, don't you? So Raja was similarly motivated with respect to doing portable execution. Okay, and I mentioned portable execution with respect to OpenMP, OpenACC, and you can extrapolate from there.
Last question.
Last question.
Quick question. Are there any plans to use Kokkos with Fortran?
So that question has come up repeatedly over the last 5 years, and let me go ahead and unplug and get out of your way. So the mechanisms with all of this template stuff and the controlling layout and using CUDA under the covers and all those kind of things, those are very C++ centric. The concepts in terms of controlling layout and controlling how things get mapped on is conceptually feasible for somebody who wanted to manipulate the Fortran language and add extensions to that. It's conceptually feasible that the OpenMP could grab some stuff and then you would get it to Fortran. It's not, as far as I know, it's not happening. The OpenMP committee, some of my colleagues are on the OpenMP committee, they're aware of the issue, but doing the data layout, I can imagine it's conceptually feasible, but pragmatically Paint would be very difficult to do with Fortran. And we probably ought to turn this one off and turn that one on.
Thank you so much.